Hello AP Calculus students, Mr. Ford here with another homework tutorial. This time we're looking at the homework for section 3.4.1, problems 147 all the way through 155, and we're going to skip 150 along the way. We'll probably also skip one or two other sections, but we'll figure it out as we go. This is kind of a rough draft for this one. 3.147 asks for the general antiderivative for each function below, and let's remember that we just learned about this in the math notes box right up above. It's the function whose derivative is the one that they give us. So we're kind of going backwards here. So for question A, I'm going to work off in the space to the side here because I think I need some extra room here. For question A, what we need is we need to take everything up a degree. So our capital F of x in this problem, question A, it needs to have a degree of x to the 6th power. We need to go up one level from there. So it's going to be something times x to the 6th. And we need that to become -6 when it multiplies in front. So -1 will do the trick there. That will be -6x to the 5th. Kind of the same thing with the second term. We need this 12x squared. We need something x to the 3rd power up there. And 3 times 4 would give us 12. So let's call it 4x to the 3rd. We'll do a plus there. And there you go. That would be the antiderivative of this thing. Of course, if we want the general antiderivative, we would also put plus c at the end because when you take the derivative, any constant number will just become 0. For question B, it's actually pretty simple because the 3 doesn't really do anything. A constant number multiplied in front will stay there when you take the derivative. And we just need to think about what function has a derivative of cosine, and that is sine. So it'll be 3 times the sine of x for our answer there. Next question, 148, sketch the graph of a function that satisfies both of the following properties. It's got to have a limit as x approaches 2 from the left of f prime of x equaling 0, and f prime of x from the right has to be infinity. Now keep in mind that these are slopes. Since we're talking about f primes, we're thinking about the slope function as we get there. We can at least sketch a little graph right now. Let's go ahead and put 1, 2, and we'll kind of put a vertical dotted line to start thinking about how we're going to make this happen. So we need a function as we approach 2 from the left side. We need the slope to approach 0. That's pretty easy to do. Just draw any curve that kind of levels off towards a slope of 0 at 2. That would do the trick. Again, you really got to be thinking about the tangent line being horizontal when you get close to 2, right there from the left. Now coming at 2 from the right, we need the slope to approach positive infinity, which means it's going to have kind of a vertical asymptote. So we really want it to be kind of like that. It can do whatever you want to after that point. It doesn't really have to be anything. Actually, my favorite way to draw this graph would be to do this, where, oh, I just deleted my x-axis. I would do something like this, where it's continuous, and you'd make it happen like that. Maybe put a sharp corner on your graph, something like that. Now, as you approach from the left side, your slope is approaching a vertical asymptote there. That would work. 149, we're going to review problem 309. On graph paper, we're going to graph the functions below, label their parts as increasing, decreasing, concave up, concave down, points of inflection, then use the first and second derivatives to determine the intervals of increasing, decreasing, and concavity. Use different colors to represent concavity. That's a lot of stuff. It might be best, well, let's see how long it takes us to do A. I think that we might just do problem A on this, and that might be enough. So I don't have graph paper here, but what we can do is we can just sketch a graph pretty quick. X squared plus 5x minus 6. It's just going to be a parabola there. But before we do any of that, let's actually analytically look at our function here. For question A, our original function is going to be x squared plus 5x minus 6. Now if we think about the derivative of that function, the derivatives will tell us if it's increasing or decreasing, if we think about it enough. When we take the derivative, we get 2x plus 5. If we use the power rule a couple times. Now, all we really care about is when this is positive and when this is negative. We could make a quick little sign chart also. Here we would represent our original function, our f of x, right there. And we could represent our derivative down here. Now, I happen to know that this equals 0. If you do the algebra really quick, subtract the 5 and divide the 2. I know that this is 0 when x is equal to -5 over 2, or -2.5. So if we put kind of a line in the middle of this right there, -2.5, let's see, anything before -2.5, like for example, if I plug in -3, that would give me a negative number in our derivative function. So it's negative on this range, and then anything after negative 2.5 will give us a positive answer, like this. What that means is that our original function is decreasing and then increasing with a change at 2.5. Looks like the vertex of this parabola is going to happen at 2.5, because that's what this is, after all. It's just a parabola. Now, if we look at the second derivative, f double prime of x, this will tell us the concavity. And the second derivative this time is actually just a constant number, 2. And the second derivative is always positive, because 2 is always a positive number, which means that our original function is always concave up, which matches what we kind of already know. I mean, this is just the graph of a parabola, and it's a positive parabola opening up because the leading coefficient is a positive number right there, positive 1. So we already kind of knew that. So if I'm going to sketch a graph of this, what I might do, I'm trying to line this up with the slope. Actually, I really wanted to keep that accurate. What I would do is I'd put 0 over here. So I could go negative 1. I'm trying to get this exactly right. 1, 2, 3, like that. Negative 3, negative 2, negative 1, kind of like that. So that negative 2.5 is kind of right in the middle there. I know that this graph is going to have, well, I could sketch a graph right now. We might actually use the calculator to get an accurate look at it. X squared minus 5x plus 6. Because I haven't graphed this in a while. I'm not really sure what it looks like. Hang on. Oh, did I get that wrong? Positive 2.5? Oh, I put it in wrong. It's plus 5x minus 6. That's why. Plus 5x minus 6. It's going to switch things around a little bit. Yeah, it's going to dip down below the y-axis a good amount. That's all I kind of wanted to know there. But it does fit that our graph is decreasing and then increasing. It's going to look something like this. Oops, let me try that again. I want it to decrease until it hits 2.5, negative 2.5 rather, and then increase like that. As far as using different colors go, I mean, this thing is always concave up. It's a parabola, so if I highlight it in green, that might work for concave up. And then decreasing would be on this little yellow range right there. And then increasing would be on this blue range right there. There you go. Pretty good. You know, I feel pretty good about the time on this one. Let's actually try B really quick. B is going to be this other polynomial function, 1/3 x to the third plus 3x squared minus x plus 5, like that. All right, now again, we want to think about our derivative function first, because that will tell us increasing and decreasing. This time our derivative is going to be something squared. It's going to be a parabola, so we'll see a little bit more of a change happening this time. If you take the power rule, 3 times 1/3 cancels out. You have x squared plus 6x minus 1, which is there. This does not equal 0 really quick. I'm going to confirm that really quick. There is, did I get that right? Minus x plus 5. This is an interesting problem. Since there is no spot, well, let's take a look here. I don't think that's ever going to be, can it be 0? I don't think it can be. Oh, it can. It will. We might actually need to use the quadratic formula or use the graph to figure out where the turning points are, plus 6x minus 1. I know you can't factor it very well, very easily. Yeah, it doesn't look like there's nice, the zeros in this one look like they are not nice answers. You know, as much as I love that, actually, since we got the graph right here, we might as well just use the graph to make a sign chart. We can just kind of estimate it. You know, I don't love problems that require me to estimate, but I'm going to go ahead and think about it anyway. F of x is going to be there's our sign chart right there. We'll soldier on, even though. I mean, here's what I know about this, is that looks like a little bit beyond, I'm guessing that is a 1, 2, 3, 4, 5, 6. A little bit beyond negative 6, there's a change in sign. So I'm going to call this negative 6. Well, yeah, I'll just call it negative 6, even though it's not negative 6. I'm just going to kind of make a sketch of the graph that way. And a little bit after 0. It's like 0.1 and negative 6.1, maybe for accuracy. We'll call it that. But we do know that this graph is positive before that, negative in the middle, and then positive after it, which means our original graph is going to be increasing, decreasing, and increasing on those ranges there. Now, if we take a look, I'm going to move this down over here. If we take a look at the second derivative now, f double prime of x, we will get 2x plus 6, which is really easy to find where it changes from negative to positive. Actually, it should kind of be the same spot on this graph. Looks like negative 3 looks to be where the derivative goes from decreasing to increasing. So x equals negative 3 is going to be the spot where it's going to change, where this equals 0. I might actually write, if I'm being more accurate, I know that f double prime of x equals 0 when x equals negative 3. So what that means up here, f double prime of x is going to have kind of a change at negative 3. And it goes from, let's see, before negative 3, it would give us a negative answer because the derivative graph is decreasing. Let's not forget those connections there. And after negative 3, it becomes positive because the couple reasons, because this number would be a positive number, and also because the derivative graph that we're looking at there is increasing. So a couple different connections there. What that means for us up here is that our original function is going to have a switch in concavity. It's increasing and concave down, decreasing and concave down, in decreasing and concave up, because it's going to switch at x equals negative 3, and then it's going to be increasing and concave up, like that. You know, the only thing we don't get from this sign chart that we're making right now is where the actual graph happens. That's more connected to the +5 that we have in the graph, but we'll talk about that in just a moment. So now let's go and sketch our original graph, and then we'll talk about concavity for a minute. If we want to sketch this, let's see. I'm going to, again, to model this, I'm going to put the y-axis kind of over here, x-axis kind of like this. Here is 1, 2, 3, 4, 5, 6. Actually, let me count that better because I want it to match what's kind of going on my sign chart there. Actually, if I think about this more, we said 0 is kind of right about here, so I'm going to make that's going to be 0, and we'll have that be kind of 6. So I'll do, there's 3, there's 1 and 2 and 3 and 4 and 5, like that. Negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6. Kind of like that. So our original graph starts off being increasing and concave down, and then goes to decreasing and concave down, which would look something, let's see. Well, it's when it switches from increasing to decreasing, it's going to have a maximum also. So our original graph is going to look like this. It's going to go increasing, and then at about that point, it's going to go decreasing and stay concave down. Our point of inflection, or our steepest slope, is going to happen at about negative 3, so they're about there. And we have a change in, that's the change in concavity happening right there. It's going to now go to concave up, and it's going to change from decreasing to increasing right around 0, where it will now go like that. I already know this is wrong because I know that the y-intercept is 5 on this graph, so I could envision sliding this whole thing up 5 steps. It's probably the same kind of graph, but looking like that. I could probably fix this by moving the x-axis down, maybe like this. Maybe like that, and then calling that 5 right there. 1, 2, 3, 4, 5, and 6. But that's kind of what's going on here. You see concave down happening on this yellow range right there. You see concave up happening on this green range here. And we've got increasing happening on these blue ranges. And then decreasing, I don't have any more highlighter colors, but decreasing is happening on this red range right there. There you go. Okay, let's move on to the next. We've been on this question for quite some time. Let's move on to the next one here. Skipping 150, let's go to 151. We're going to state the domain and the range of each function below. You could use a calculator for this, and that would probably be a good thing to do, but we'll at least pick out the domain right away. I could factor. Can I factor the top? I can. It would be x minus 3 and x plus 2. I think I got that right. Over x plus 1. Well, I know right away the domain is that x cannot be 1. Domain is all x's such that x is not equal to negative 1, because that would cause the asymptote to happen. And I think that since the degree on top is higher than the degree on bottom, I think the range is probably going to be all real numbers. That one might just be one I have to graph to see it. Let's see. On the top of my fraction, I'm going to graph this really quick. On the top, we have x squared minus x plus minus 6. On the bottom, we have x plus 1. And taking a look at the graph really quick, I suspect we'll see all real numbers here, but it's possible that we won't. Yeah, it's going to be all real numbers. Range is all real numbers. For graph B, in this one we have the same top there. We have x, what did I say, x minus 3 and x plus 2? Yeah, it's same as the last function, only the bottom is changed to x plus 2, which is going to kind of cancel out. It doesn't actually cancel out. What happens here is the domain is the same. The domain is still all x's such that x is not equal to 2, or sorry, negative 2 rather. But now the graph is going to look exactly like the graph of just x minus 3 on its own, which is just a linear function. However, we should remember that on this graph there's going to be a hole at x equals 2. And what would happen if we plugged in 2 to the problem, 2 minus 3 would give us negative 1. So the range on this function can never actually output negative 1 because there's going to be a hole at the point negative 2, negative 1, which is right about, I think I got that. Oh, sorry, it would be negative 2, negative 5, my fault. Which is going to happen right about there on calculator cam. There's going to be a hole there. So the range is all y's such that y is not equal to negative 5. That would be the case there. Pretty cool. Okay, moving on to the next question. Write an equation for z prime if z of x is 3x squared plus 5x plus 1, and then write the equation of the line in tangent line in point slope form at x equals negative 2. Okay, so for the equation for z prime, what we would need is, well, this is the power rule. Z prime of x is going to be 6x plus 5. That's it, if I follow the power rule. Now, if I want the equation of the tangent line in point slope form, let's review point slope form really quick. The AP Calculus version of point slope form is y minus f of a equals f prime of a times x minus a. In this case, we're kind of given that our a is negative 2. That's what they told us when they wanted x to be negative 2. So we kind of have to go shopping a little bit. We first need to know what z, the original function, is of negative 2. That would be 3 times negative 2 squared plus 5 times negative 2 plus 1, which in this case would be 3 times 4, which is 12, minus 10 plus 1, or 3 in the cases. So this number will become negative 2, this number will become 3, and we also need to know f prime, or z prime of negative 2, which is just going to be 6 times negative 2 plus 5. In this case, that would be negative 12 plus 5, which is negative 7, and that number is going to go right there. So our final answer for this slope of the point slope form would be y minus 3 equals negative 7 times x plus 2. And that's all you do. I would not take that to the next stage. 3.153, we have another interesting kind of drawing problem. We have to sketch a continuous curve which meets all of the following criteria. Its slope must be positive, which also means the graph is increasing. It has to be concave down the entire time. We have a point on it. The point 2, 1 needs to be on the graph, and the slope at 2 needs to be 1/2. So let's start with this point of 2, 1. I'm just going to sketch really quick what's going on here. Point 1 to the right, 2, up 1. Put a point right there. Now that takes care of this part of it. That's done. As far as the derivative at 2 being 1/2, I think what would be a good idea is to, kind of zooming in on this point, is to make a little slope triangle that has the slope of 1/2. Like go down 1 and back 2. Or maybe to the right 2 and up 1. And just kind of like sketch in a little secant line. Like whatever the curve that we're going to draw is doing, it has to have that line as a tangent at that one point. We also know this graph has to always be increasing and concave down. So I think the best way to do this would be to draw kind of an exponential curve, kind of like this. There you go. It's always increasing, it's always concave down, and it has the other qualifications. So I think that takes care of it. There's some other questions there. How many roots does it have? Well, I see 1. I don't think you can draw any more. You have to be constantly increasing, so that's that. What can you say about the location of the roots? I don't know. That's kind of nebulous. I can draw this curve pretty much any way. I guess it has to be less than negative 2, less than 2. Because it's got to be above the x-axis at 2, 1. So it has to cross, since it's increasing, it has to cross the x-axis before 2. What is the limit as x approaches negative infinity of f of x? Well, it's negative infinity. And I think that has to be the case since this graph has to be increasing. If you go back in time, it has to go decreasing. Is it possible that f prime of 1 equals 1? I think that's possible. I think my graph actually kind of looks like that. I think that's a yes. Would it be possible for f prime of 1 to be 1/4? I think it is possible too. It just depends on how steep or shallow you want to make that curve. I think it does. I don't think it matters. I think you could totally do either ones. As long as it's positive, because we have established that f prime of x has to be greater than 0. So f prime of x could be any positive number. That's otherwise, then there's no reason why it wouldn't have to be that. Now, I'm going to run out of time for this video here in a moment. We already crossed the 20-minute mark. I do want to make a separate video for 54 and 55, but I'm going to pause this presentation right now and come back and do 54 and 55 later in a different video. So thanks for watching. Don't forget, you are awesome. Keep it up and let that struggle happen, because this is tough stuff to be doing, and certainly as you get more practice with it, you'll get a little bit better at it every single time. All right, I'll see you in the next video. Peace.